Hopefully you're doing well. In this video, we're going to continue with chapter 4, probability. Remember, in this section, we already covered a few of, on this chapter, we already covered basic concept of probabilities, addition rules, and multiplication rules. We covered complement conditional probability in section 4.3. Now we're going to continue with section 4.4, uh, counting, where we would attempt to develop the ability to apply the fundamental counting rules, factorial rule, permutation rules, and combinations rules, and we would try to see how we can distinguish between circumstances requiring the permutation rules and those requiring the combinations rules. So remember, one that required orders, the other one that doesn't. But because you like it so much, we're gonna focus and do as many as possible. So, look at the key concepts we're going to cover, especially here. The key concepts is very important, right? Let me verify very quick from the book what planning on doing. The counting principles is mostly what we gonna do. All right. So see the key concepts right there. What you can tell me what you see. These sections require a grid. I'm still looking for this one from the book. Yeah. Probability concept typically requires that we know the total number of simple events. Okay. So this section requires much greater use of formulas as we consider 5 different methods for counting the for counting the number of possible outcomes in a variety of situations. Remember, counting is very important. We remember in section 4.2 with the addition rule, multiplication rule, and conditional rule, we encourage you at that point to use intuitive rules based on understanding, and we discourage blind use of formulas for that, right? Because sometimes use of formulas may lead you to incorrect answers, but doing intuitive rules is also important. So this section requires that not all counting problems can be solved with these 5 methods. So that's what we want to show you here. But they do provide a strong foundation for the most common real application. So that's at some point a lot of things that we want to cover. We start with the multiplication counting rule that is used to find the total number of possibilities from some sequence of events, right? So at some point, we can say that for a sequence of events in which the first event can occur n sub 1 ways, the second event can occur n sub 2 ways, the third event can occur n sub 3 ways, and so on. So the totals, you can simply multiply them. For those of you who forget, for example, I'm gonna just go with factorials rules. Remember, for the factorials, very important, the factorial rules is used to find the total number of ways that n different items can be arranged. Order of items matters. Of course, the factorial rules, like we use dot symbols. Like if we said 5 factorials, you can read it 5 factorials, meaning if you do 5 factorials is 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20 times 3 is 60 times 2, 120. So that will be the answer for it. So remember the factorials are very, very important when you deal with probabilities or when you use permutations or combinations. That's really important. So the factorials rules is really, factorials rules is based, factorials rules is, factorials rules is based on the principle that the first item may be selected n different ways. The second items may be selected n minus one different ways, and so on. So this rule is really the multiplication counting will modify for the elimination of one item on each section. So as we said, if you do the only by conventions, if you see 0 factorials is equal to 1, because we don't want you to see like something, let's say 5 factorials over 0 factorials, that's equal 5 times 4 times 3 times 2 times 1 over 1. So 120 over 1 is 120. But remember, 5 factorials over only 0, any number divided by 0, it would be undefined. It's undefined. You cannot divide by 0, but if it's a factorial, if it's 0 factorials, then that's by convention or by special definitions. It is what it is. Whatever you see, it is. Okay. So factorials are very important, and we cannot do anything without using these rules of factorials. Now, permutations, we have different ways of seeing permutation, because permutation in itself, when you have an order of n objects, the permutation is an ordered arrangement of objects. The number of different permutation of n objects is n factorial. So we said in terms of permutations, we have different ways of seeing it. Permutation of items are arranged in which different sequences of the same items are counted separately. Okay, so remember, we're gonna do that. The letter arrangements of ABC, ACB, BAC, BCA, CAB, and CBA are all counted separately as 6 different permutations. So that's why, as we said, the permutation is an ordered arrangements of objects. The number of different permutations, we call it n factorial. So number of different permutation. Okay, number of different permutations of n distinct objects, of n distinct objects is n factorials. Remember, if you see n factorials, is like for us is n times n minus 1 times n minus 2 times n minus 3 until you get to times 1 times 1, okay, times 0 factorial if you want, or you can stop at 1 factorial. So, right, 1 factorial is 1, we can go there. So we know 0 factorial is 1, okay? Factorial 0 is 1. So combinations, we're gonna go back again for permutations, but let's go for permutations. Permutations are, we can consider also there is a formula for permutations. We're gonna go back to it. See, you may want to choose some of the objects in a group and put them in order. So such as order. If it is an order, if you take, you call this permutation of all objects, taking all at a time. If there is order, okay, if there is order, then you should see, what it is. We're gonna come back to it in a few minutes. But for combinations, we said combinations of items are arranged in which way, in which different sequences of the same items are counted as being the same. You see, for permutation, different sequences of the same object are counted separately. But here, if you do combinations, then it's like you consider it as the same. Okay, so the letter arrangements of A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A are all considered to be exactly the same. Okay, so there is no such permutations. You can only say you have three of them. However, for the previous one, you said you have eight different ones. So remember, permutation position, where the alliteration reminds us that with permutations, the position of the items makes a difference. You cannot change the order. If you want to form a committee of three members taking out of eight students, these three members must be president, vice president, and secretary. You cannot switch the position between president and secretary. The president comes first, vice president comes second, and the secretary comes third. So that's permutation. Now, if you want to see it for combinations, because they are all the same, you only form a committee of three members and you don't identify which one could be president, vice president, and secretary. So at this one, you only have this particular choice, only three of them you can become. So remember, combination committee, which reminds us that with members of a committee, rearrangement of the same members result in the same committee, so orders that matter. So we only said in that committee we have only three members. So we're gonna consider it this way. All right. Let's go with some formulas that we definitely need to use, because when we talk about permutation, we said the permutation rules is used when there are n different items available for selection. We must select all of them without replacement, and the sequence of the items matter. So the result is the total number of arrangements, permutation, that are possible. So remember, we said rearrangement of the same items are counted as different permutations. So what we mean by that, as we said, if the number of permutation of n objects taken are ordered at a time, remember ordered, they must be ordered objects. So this is the formula for it. This formula we're gonna use, we have a formula we can use when n items are available and r of them are selected without replacement. Okay, the number of different permutations are given by this formula. So let's say if we do let's say 7p3. You have seven people and you want to form a committee of three members, and from which these two members are president, vice president, and secretary. Because there is an order, we must use permutation. Now, how we would do it? Because we said NPR, that means for us here, N is 7 and R is 3. So if you follow these formulas, because we said it must be n factorials over n minus r factorials. Now let's simplify the denominator. It's give you 4 factorials. The only way you can simplify factorials with factors. So remember, 7 factorials for us is like 7 times 6 times 5 times 4. I can go up all the way to 1, but because I see 4 factorials in the denominator, I know I can simplify by 4 factorials. So if I cancel these two, so I only have 7 times 6 times 5, okay? And 7 times 6 times 5. We must see it in this corner that way. So 7 times 6 times 5, we know the answer would be 210. So, how many different ways you can form a committee of three members from seven students where you have president, vice president, and secretary? There are 210 different ways to do it in order. But if you do permutations, if you do combinations, of course, it's going to be different. So permutation rules, when some items are identical to others, we call it distinguishable. So the number of different permutation orders counts when n items are available. When n items are available, so what we can do then, when and all n of them are selected without replacement. Remember, without replacements, of course, we know that would be permutation. Okay, without replacement, it would be permutation. And in this case, what we need to do, some of the items are identical to others. It's found by n factorials over, and you can take them, each, those that are repeated items form it. So, for examples, we call this one also distinguishable permutation of n objects where n sub 1 are all one type and n sub 2 are all one type and n sub 3, etc. So we can write it this way. For examples, let's suppose, if you have something where you need to uh, choose desert, or let's say a contractor builder is planning to build a subdivision. This subdivision is to consist of 6 one-house stories, 4 two-house story, and 2 split level house. In how many different distinguishable ways can the houses be arranged? 6 plus 4 plus 2, that make it 12. So the 12 would be on the top like this, and you have the 6, because I said you can do a 6 one-story and a 4 two-story and 2 lower levels. So for example, you can do that. You see, if you add up the numbers in the denominator, it's equal to the number in the numerator. All right. So that's how we're going to do it when it is all distinguishables. Now, combination rules, remember we said permutation, you have everything in order. You want to form a committee of three members from seven students. All those, these three committee members should be president, vice president, and secretary. That means they are in order. But when you deal with combinations, it would be a little bit different. I'm trying to cover all the rules with you right now so we can focus on doing exercises after. So combination rules, the combination rules is used when there are n different items available for selection. Only all of them are selected without replacement, and others does not. Okay, matter. So there is always a total of total number of combinations that are possible. Remember, like here, rearrangements of the same items are considered to be the same combination. So we see when n different items are available, but only all of them are selected without replacement. So the number of combinations is found by this formula. So you see, we do NCR, right? You see n factorials over n minus r factorial. Don't forget the factorials, r factorial. For example, if we take the same one we did for permutation, instead of, remember we said, if you do 7PR, we found it was 210. But also, if you do combinations, 7CR, that means 7 factorials over 7 minus 3 factorials, 3 factorials. So R. Remember, N is 7 and R is 3. So if we go 7 factorials over 4 factorials times 3 factorials, remember that we have 7 times 6 times 5 times 4 factorials. If you want to go all the way down, it's fine too, right? And we have 3 times 2 times 1. Now, look what happened. If I cancel the 4 factorials, we can only cancel 4 factorials, 4 factorials. So we have 7 times 6 times 5 over 3 times 2 times 1. Now, remember, you can say the denominator is 7 times 6 times 5 over 6. If we cancel the 6, we have 7 times 5, which is 35. You see? So the number of ways you can choose 3 members of a committee out of 7 students, it's 35 different ways because we don't put them in order like president, vice president, secretary. We only say we need 3 members for that committee. Then we go with combination. So as we said, the number of combinations of R objects select from a group of N objects without regard to order, we don't pay attention to reorder. But permutation, you must follow the order. Combinations, you don't have to. You don't have to. So that's what make the difference between these two. Let's see very quick all these examples we can do very giantly quick that you will definitely enjoy and doing. Okay, so the first examples, we're planning on doing here is, they said, I'm gonna try to reduce the font. Let me put it 14, so we have enough space. Okay, what do we mean? Enter, 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 enter. Okay, feel like I have enough space for each of them. Okay, for number 1, it said that use it ATM ATM cards and hotels safes typically require the 4 digits. Okay, usually we do it 4 digits code, right? 4 digit codes. Remember, digits. How many digits do we have? Number of digits. Yes, 0 to 9 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You have always 10 digits. Okay? Such codes like 3, 2, 1, 2. You see, you can have repeated digits. Digits can be repeat, but they must be entered in the correct order. If someone gains access, okay, and enter a code that was select a code that was random selected, what is the probability of getting the correct code on the first try? Right? So you have 10 digits, right? You know you need to do it a 4 digit code. 1, 2, 3, and 4. 4 digit. Okay, 1, 2, 3, and 4. All right. Now, 10 digits, what is the probability of getting the first digit correct? Yeah, the probability of getting the first digit correct is very simple. It's 1 out of 10 because you have 10 digits. So 1 out of 10, that's the probability of getting the first one correct. What is the probability of getting the second one correct? 1 out of 10. Remember, they said you can repeat. If they said we couldn't repeat, then we would take the probability of getting the first one correct would be 1 out of 10. The second one would be 1 out of 9. But they said we can repeat them. So the probability of getting the third digit correct is 1 out of 10 again. And the probability of getting the last digit correct is 1 out of 10. Because they said on the first try, they do it and the answer could be correct. You know, when you have fraction times fraction, you multiply the numerators together and multiply the denominators. It puts it into 10,000, right? So that's the probability of getting the correct code for your ATM card on the first try. I mean, for someone to do it. All right. And of course, we can do the same for number 2 because the number 2 said the social security number consists of 9 digits. Okay. 9. digits, okay, in a particular order, okay? And repetition of digits is allowed, so you can have them, yeah, all of them. After seeing the last four digits printed on a receipt, okay, because you already know the last four digits, remember there should be nine digits: one, two, three, four, five, six, seven, eight, and nine. One, two, three, four, five, six, seven, eight, nine. So we're gonna consider like the nine digits for the Social Security card. Those are the nine digits. They said you already know the last four. You know the last four. What is the probability? Okay, okay. What is the probability of getting the correct social security number of the person who has given the receipt? You know the last one now. How many you want to guess? Yes, five of them. Now you need to only guess five of them. One, two, three, four, and five. Very easy because you know the first one is out of 10, correct? The second one is out of 10, correct? The third one is out of 10, correct? The fourth one is out of 10, correct? The fifth one is out of 10. If you try and you get it correct, and that will be the answer for it. So at this point, because you already know the last four, you only need to get the first five. So that gives you 100,000. You know, so the probability is very, very low, but at some point you need to guess it. All right. So that's a beautiful example. And if you want to continue, we can definitely do that. Okay. So look, number three, in the FIFA Women's World Cup 2019, a tie at the end of two overtime periods leads to a shootout with five kicks taken by each team from the penalty mark. Okay. We have five of them. Yeah. Each hit must be taken by a different player. How many ways can five players be selected from the 11 eligible players? Well, the first thing you need to verify here is the order matter. Do you need to be like, oh, number nine, take the penalty kick first? No, the order doesn't matter. If the order doesn't matter, which one would you use? Permutation or combinations? If permutation, remember, if it doesn't matter, then you should go with combinations. Now we're gonna say we have n equal 11 and r equal 5. So meaning you said NCR, remember is n factorials over n minus r factorials and r factorials. So meaning we're going to have 11C5 would be 11 factorials over 11 minus 5 factorials times 5 factorials. Now, if you do 11 factorials over 11 minus 5 is 6 factorials times 5 factorials. Now let's go. We do 11 times 10 times 9 times 8 times 7 times 6. I'm going to cancel 6 factorials because at this point I see 6 factorials. You can only cancel factorials with factorials. So we continue with 11 times 10 times 9 times 8 times 7 over 5 times 4 times 3 times 2 times 1. Now we know at the end our beautiful answer would be 462. But of course, if we look at the calculator, let me grab a calculator, TI-84 or any of these TI. Remember what we need to go look for on your calculator, the distributions. Okay, so I mean, there is this on your calculator. You have on your calculator look for this on your calculator and see. Two different places to find. Let me there you go in math, and then I mean for TI 83 and 84, math, and then you look for probability, then you can do it. Okay, that's very important. In a different video, I'll show you how to do it using TI 84, TI 85, or TI 89. So look for me for a different video on how to use calculators to perform some combinations and permutations. Now, this said, how many different ways can five players be selected from the 11 eligible players? And also, for the five select players, how many ways can they be assigned as first, second, third, fourth, and fifth? So very simple. Remember, you have five players you want to assign as number one. If you know this part right here, and I put it here is 5 factorials. And how do you do 5 factorials at this point? Is 5 times 4 times 3 times 2 times 1 is 120. All right. So how many different ways can the assign first, second, third, fourth, and fifth? 120 different ways. Now, in the calculator, also make sure you check for n factorials because, oh, sorry, I do it manually here, but of course you can do everything using calculator. How many different ways can the letter statistics be arranged if the letter statistics are arranged in in a random order? What is the probability that the result would be statistics? But the first questions, how many different ways? Maybe they should do in some books or in some textbooks, you would say how many distinguishable ways. Okay, now they said how many different ways can the letters be arranged. The first thing to do, if you remember that rules of spatial permutations we covered, where did we cover it? I believe we covered it spatial permutations right there. So permutation rules, the number of n of different permutations, or when you do it without replacement, when there are repetitions. So that's what we're gonna do here. The first one is to count the number of letters. Okay, let's count the number of letters in the word statistics. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know that should be 10 factorials. Now, over repeated ones. How many S's do you see in statistics? Yes, we have 3 S's, 3 factorial for S. How many T's? 3 T's in statistics. How many A? We see 1 A, but doesn't matter, we put it. How many I's? 2 I's. And how many C's? 1 C's. So if you want to rewrite it, is that for us 10 factorials over 2 factorials, 3 factorials, and 3 factorials. And you know how to go from 10 to, you can go 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 factorials. We can cancel at 3 factorials, but 2 times 1, 3 times 2 times 1, 3 factorials. If we cancel the factorials right there, 2 times, remember, 2 times 3 is 6. So we can cancel 6 and these 2. And we can also cancel 2 and 4. So we have a 3 here left. So we have 10 times 9 times 8 times 7 times 5 and times 2. If we multiply all of this, it must give you 50,400 distinguishable ways to do that. So the question is, if the letters of statistics are arranged in a random order, what is the probability that the results would be statistics? This is one possibility, is one out of all of this. That's the answer, would be the one out of 50,000. That's the probability. Probability, right? Yeah. All right. So that's our first examples here, and I mean four different exercise. It is we were warming up, and hopefully we're gonna go faster in the next ones because we're gonna continue doing more exercise, more exercise till the end. Now we said for the next examples here we have plenty of them. All right, we can start with the presidential. Okay, let's start with a presidential candidate. Okay, and that would be a presidential candidate plans on to begin her campaign by visiting the capitals of 4 out of 50 states. If the four capitals are randomly selected without replacement, oh, without replacement, you hear that? Without replacement. That means what again? Permutation. What is the probability that the root is Sacramento come first, Juneau second, Hartford third, and Bismarck fourth? So it is in order. In this case, you need to go with NPR, that's permutation. So this one must be permutation. Right? So if you do permutation, then that would be, remember, NPR is n factorials over n minus r factors. Or just go on your calculator and look for in the probability NPR. It's much easier. So you enter the numbers in order because in this case, n is 50 and r is 4. So if you do NPR, sorry, we do 50p4, 50p4. So that means 50 factorials over 50 minus 4 factorials. So that means 50 factorials over 46 factorials. So we can go all the way from, as we said, in this case, we can go all the way from that number, like you do 50 times 49 times 48 times 47 times 46, and all of this on over 46 factorials. So when we cancel factorials, remember we can cancel factorials. When we cancel this, when you have the 50 times 49 times 48 times 47, it gives you a big, giant number. And this number is, remember here, we only find the different ways of doing it. So the different ways would be, if I erase, you know what, I'm gonna erase this and make it shorter. Okay, you know what, let's do it. We know that would be, what number it would be again? 5 millions, correct me if I'm wrong. Two, no, 5 million, 527,200. That's the number of distinguishable way. Now, the questions, what is the probability? What is the probability again? The probability must be 1 out of 527,200. Okay. So for me, the probability would be 1 out of 5,527,200. So that would be the answer for the probability. The question was find the probability. We're gonna try to do the next by making sure we follow it properly. You know what? I'm gonna do copy paste so I can construct have more space for that. Let's erase everything here and everything here and everything here. So because I'm done with the first one, I create enough space for the others. Let's try it. Or we may not need to do all of them, right? Okay, these are the two. Okay. Now, when testing for the current in a cable with 5 color code wires, the author use a meter to test 2 wires at a time. You see that? You do it to test two at a time. How many different tests are required for every possible pair of 2 wires? Possible pair. How many colors we have when testing for current in a cable with 5 color code wire? So if you make it in pair, pairing means by 2, right? So meaning it would definitely be 10 in totals, right? So N would be 10, while R would be 2. Now you need to decide, would that be combinations or would that be permutations? Because there is no order, it would be combinations. Remember combinations, NCR, it's N factorials over N minus R factorials times R factorials. 10C 2 would be 10 factorials over 10 minus 2 factorials, 2 factorials. But by now, you can either do it manually or use your calculator. I'm expecting everyone to use calculator, like 10 times 9 times 8 factorials over, we do 8 factorials times 2 times 1. We can cancel the 8 factorials. We cancel the 2. Okay. So cancel the 8 factorials and cancel the 2. Is that correct? Um, that would be at some point, that would be right. That should be 5 times 9 is 40, right? Because the questions ask, let me verify very quick my notes, okay? Because in this case, should be something very simple to do, yeah? So remember, the order doesn't matter as we can see, okay? So finding these numbers make it very easy. We may want to know how many unique pairs you can find. So we said it should be pairs. If you have 5 pairs, that make it 10. So we have, oh, yes, you are correctly correct on this. That should be only, I don't know why I put 10. It's 5 because they already do 10. Apologize for this. That shouldn't be 10. Okay. I apologize. So we have N equal 5 and R equal 2. So if we do 5C2, it is 5 factorials over 5 minus 2 factorials times 2 factorials. So we have 5 times 4 times, no, let's show this one first because we have 5 factorials over 3 factorials times 2 factorials. 5 times 4 times 3 factorials over 3 factorials times 2 times 1. If we cancel the 3 factorials, that make it 5 times 4 over 2. 20 over 2 is 10. Okay, so in this case, that would be only 10. We need 10 different pairwise tests to cover all combinations. So I think that's something we were supposed to think about. Of course, we were supposed to think about it. Now, let's go back and answer some very important questions according to number two. I'm hoping we have enough space for number two because in number two, we said as of this written, the Powerball is running in 44 states in the United States. Winning the jackpot requires that you select the correct five different numbers from 1 to 69. So, should that be in order? One thing I don't, you need to pay attention to, I am not sure the five different numbers, you need to take them in order. So, meaning that would be combinations when you know n is 69 and you have also R would be five different ones in a separate drawing. You must also select the correct single value. Remember, there is another value. For those of you who play, it's 5 plus 1, right? That you need to select from 1 to 26. Find the probability of winning. First of all, before you even find the probability, you need to calculate the number of ways to choose the five digits. So, it's a combination. So, we're going to do it's combination. So, we're going to do 69 combinations of 5, something you should be doing like 69 factorials over 69 minus 5 factorials times 5 factorials. Now, because you know how to do it, I'm not gonna lose enough time because I do it with my calculator. It give me 11,000 millions 238 thousand 513. All right, but remember also, you must choose the extra number by multiplying it with the extra number because they said calculate the number of ways. You need to multiply by the number of Powerball choice because there are 26 possible Powerball numbers. So you must pick up exactly the right one. So we need to multiply it. So total combinations multiply by 26, the 26 Powerball, right? Because you must do it with the Powerball. So you end up with 11 million 238,513 times 26. That gives you a big giant number. So what this number would be when you multiply with 20 with that big giant number is give you 292 million 201,338. All right. Now this number right there is the number of different ways you can win. Now, what is the probability of getting the of winning then? It's one out of that number. Probability of winning the Powerball, probability of winning is one out of that big number. So you can do it in your calculator, of course. 292,201,338. When you perform your divisions, you should find this answer, right? So you should find this answer for winning the Powerball. So it would be this, and you can definitely use a calculator to find it in terms of you know That's that's a lot of work, you know. So to do that, the probability of winning the jackpot is one out of that number. So your odds about like one out of 292 million time, So just respect whoever win the Powerball already. But let's go with the next one because there are so many different ways we can solve those type of problems. For number three, if you randomly select 5 digits, each digits 0 to 9 with repeated allowance, what is the probability of, you will get the other zip code? I think we did an examples like this before, right? So the probability of getting the other's zip code, that should be something, very simple because, as I said, feel like we did something like that before. Oh, we didn't do it for the zip code, but we did it for, you know, uh, you know, the zip code, remember, is 5 digits. That means 1, 2, 3, 4, and 5. So remember, to obtain the zip code, the first digit can be anything from 0 to 1. That means 10 possibility, 10 possibility, 10 possibility, 10 possibility, 10 possibility. Remember, they said you can do repeated digits. If you multiply all of this, answer would be 100,000. What is the probability then of doing it on the first try? Yes, is 1 out of 100,000. So that makes those very simple to do. 1 out of 100,000. That's a probability. Of course, that gives you 0.0001. That's a very light. Just to randomly select the probability of randomly select the 5 digits for the zip code of the author without knowing it. I need to add without knowing it because some people might know it, but you don't know it. All right. Let's go with a bigger examples because as we move forward, probably we need more work to do. All right. In this one, what they ask you to do, let's go with these examples very quick. Okay. What they ask you to do, you want to obtain cash by using an ATM machine. But it's dark and you can't see your card when you insert it. The card must be inserted with the front side up and the printing configured so that the beginning of your name entered first. Okay? So remember, first card. Look at that. What is the probability of selecting a random position and insert the card with the result that the card insert correct? How many different possibilities you have? If you enter the card with face up, but the first name entered first, okay, that's the first possibility. Remember, face up, first, correct, face up, plus, name after, and correct. Okay, is that the two? No, you can also, because it's dark, you don't see. Maybe you would also enter face, no? Face down, right? Name first. Also incorrect. And you can also enter face down, name after. Also incorrect. The only times it's correct is when you enter name first. So you see that you have 4 different possibilities. So if you answer the first question, what is the probability All right. What is the probability of selecting random position and insert the card with the result that the card is inserted correctly? It's only 1 out of 4 of the time. So 0.25 or 25% of the time. That would be the only time because there are four possibilities. Either you enter face up need first, that's correct, or the other three times are incorrect. What is the probability of randomly select the card's position and finding that it is incorrectly insert, but it is correctly insert on the second attempt? Assume that the same position used for the first attempt could also be used for the second attempt. So that's where it's become a little bit complicated. Probability incorrect. What is probability for incorrect to prob? For incorrect, what would be that? Yes, that would be 3 out of 4 because there are four possibility. That's 0.75 or 75% of the time. But because what we said is like because what we said is like we have the probability that you answer the card correct and the probability you answer the card incorrect. What they asked you to do as a questions, find the probability that you enter incorrect first, then correct second. So if you do that correct seconds, remember. So that would be 3 out of 4 times 1 out of 4. If you multiply, remember that gives you 3 out of 16. Do not add, you need to multiply. So doing this, you can divide. Okay, so 3 divided by 16, that gives you 0.1875, or you can say it's 18.75% that you can enter it, this way. Now, the next questions in this, so they ask you, how many random selections are required to be absolutely sure the card works because it is entered correctly, right? Because how many random insertions are required to be absolutely sure the card worked? I mean, it's entered correctly. Well, you need to do all four of them, you know. How many random selections? Four. You need to do all four, right? If you do all four, that's a tricky question because, of course, we can say there is no finite number of attempts because you could continue to get the wrong position every time. But at least, you know what? There are four positions. You try all right? To be absolutely sure, you try every possible one. You must try all four. So try all four. Three, try all four. Even though all four position, even though you try all four, doesn't mean it's gonna get come out correctly. So that's something, as I said, this is something very tricky to verify. Now, let's see another examples. I don't know how many do we have left, probably two. Um, you become suspicious when a genetic researcher randomly select numerous group of 20 newborn babies and seems to constantly get 10 girls and 10 boys. The researcher claims that it is common to get 10 girls and 10 boys in such case. Right? Let's go through this one and see what's going to happen. They said that if 20 new babies are randomly select, how many different gender sequences are possible? So we have 20. Each baby is equally likely to be a girl or a boy. It can be 10 girls, 10 boys, or 20 girls, 0 boys, or 20 boys, 0 girls, or 15 girls, 5 boys, it's like a fair coin toss, right? It's like you flip a fair coin. right? So for 20 babies, we assume binomial model. So let's say it's equally 10-10, right? Probability that you obtain a boy is 50%, 1 out of 2. Probability you obtain a girl is 50%, right? So how many different gender sequences are possible for 20 babies? You know, it's definitely um, one. It's definite. Oh, we're gonna do it like we can do it. It's 2 power 10. Is 2 power n, right? What is n? N is 20, right? So 2 power 10, power 20, so 2 power 20. So if you do 2 power 20 in a calculator, it should give you 1,048,576. 1,048 5 7 6. So that's the first answer. As we said, we want to make sure that each baby can be either boy or girl, and the order matters. So we're gonna do it this way. Okay. Very important to verify and the in this second questions second questions how many different ways can 10 girls and 10 boys be arranged in sequence? This is the number of permutation of 10 girls and 10 boys. You can do permutations, you know um in 20 positions. So if we do, as we said, permutations, you can do for number 2. Let me put number 2 here. It should be 10 boys, 10 girls. So let's say it's a 10, no, 20, because n is 20. I forgot. It's 20 p 10, right? So if you do this, unfortunately, let's see if my calculator here can do my permutations. NPR, right? I'm gonna just verify it. It's definitely a combination. So I don't know why I said permutation. There is no order. The order doesn't matter. It's combinations. 20 C10. So if we do 20 C10, remember using manually, it should be 20 minus 10 factorials times 10 factorials. And answer in this case, the answer in this case, what would that be? When you do that, the answer would be 184,756. Number 3, what is the probability of getting 10 girls and 10 boys when 20 babies are born? Right? Remember the first one we said, how many different ways can 10 girls and 10 boys be arranged in sequence? We use combinations. But in this one, it would be a little bit different because we said uh, the probability of getting 10 boys and 10 girls, we need to do it in a different way. So we have the C3. At this point, probability of getting 10 girls, 10 boys would be the combinations, you have over the big total. So for us, it's like 20 C10 over 2 power 20. So if you do that, answer would be some big numbers like you have 184,756 over the 1,048,576. And in this case, you can find only 0.176 or 17.6%. Okay, you can either use both. So number 4 is the researcher on the preceding results, do you Based on the preceding results, do you agree with the researchers' explanation that it is common to get 10 girls and 10 boys when 20 babies are born? Look at the percentages. You know, uh, what's common? Probability is only 0.176. You know, of course, but it is not close to 50%. It's something very special, with a probability of 0.176 or 17.6%, the result is common, but it should not happen consequently because it's pretty far it's pretty far from 50%. So we cannot say that. So most of the time, the number of girls and boys will not be exactly equal, right? So sometimes might have 9 boys and 10 girls, 11 girls, or 12 girls, like 8 boys. So we cannot say that. So it's not unlikely, it's also not typically. So the most probable single outcome is 10 girls and 10 boys, but it is still just one of many different outcomes, right? Let's try the last one, or let's leave the last one for you because you can see it's very similar to what we had before, all right? Because we did the parables. If you see this, I'm definitely gonna let you enjoy these examples because oh, we can do it very quick because if you have 70 numbers and you want to select five, you already know if N is 70 and R is five. So for the first one, what is the probability of winning the tickets? First of all, you need to know how many different ways. If you do 70 combinations of five, that probably would give you a big number from your calculator, which is 12,103,014. But remember, you need also, and in a separate drawing, you must also select the correct single number from 1 to 25. Whatever you find here, you must multiply it with 25. So because you multiply by the 25 possible mega millions, so this number and this fall in itself would be 302,575,350. Now, when they ask you probability, what is the probability of winning the tickets? To get the winning tickets, it's only one out of that number. Yeah, you know. And yes, that's the probability of winning. Of course, the questions they ask you, how does the result compare to the probability of being struck by lightning in years, which is the national survey estimate to be? So you couldn't do your own research on it, but last time I checked, we said probability you get lightning. So I believe probability you get lightning, probability of lightning is 1/22200. Look at that. Compare these two. Do you believe that how does the result compare to the probability of being struck by lightning in a national in a year, right? I think it's much closer, right? So because the National Weather Service estimate the annual probability of being struck by lightning in the US is 1/1,222,000. Okay. But if you compare these two, the way you can compare them is to divide, you know. So for us, divide if you divide the probability like 1/350,575,350 over 1/122,200. Now taking this multiply the first fraction by the reciprocal of the second fraction, it would be 1,222,000 over 302,575,000, and we said 350. That would give you 0.0404. So you are very far, like if you multiply it. I mean, it's faster to get stuck, you know. It's faster to get stuck by the lightning, you know. There is much better chance, you know, there is much better chance, right? Uh, of being struck by the lightning, of right there. Because look, 1 out of 300 millions and 1 out of 100 million. So you have better chance of get struck by the lightning. So number three, we can see the last questions, and they ask you something very simple. You know, they ask you, how does the probability compare from the from the uh, to the probability of the old mega millions? At that point, you only have 15 digits. Now you have 25. All you need to do is count, multiply by 20, by 15 for the second one, and compare it with the first one, and you will see the result. Hopefully, this helped. Remember, in a different video, I would cover on how to do these probabilities using either Excel, or we would use um, TI-84. Take care. I'll see you in a different video.